So I was asked to give a little bit of a discussion here on life cycle cost analysis. So in the previous presentation with Joe, he put up a lot of prices, which I think is fantastic because it's so unusual to see all those prices in one place and be able to see one right next to another. And what I'm going to do is I'm going to talk about not only initial prices and not only initial materials or agency prices, but also putting agency and user costs together and then seeing how over a timeline, over a 50-year timeline, we can look at costs. And what we did is we specifically focused on full depth reclamation as an alternative to some of the traditional maintenance and rehabilitation activities in the state of Arkansas. The motivation for FDR is that in the state of Arkansas, we do have a lot of rural highways. A lot of these rural highways were not designed for heavy loads. We've had a lot of natural gas drilling in the state, and we also have quite a bit of logging in the state. So you have these very heavy trucks, relatively high frequency, going over these roadways that were not designed for those type of loads. And in the state of Arkansas, they have a relatively small toolbox that they use for pavement maintenance and rehabilitation. I was very jealous of Chisago County's toolbox. They use a lot more tools. In the state of Arkansas, we use a chip seal, a 2-inch overlay, a mill and fill, and a remove and replace. And that's pretty much all we use, which is unfortunate. So I spent a lot of time trying to talk to AHTD, now RDOT, about what other options are out there, because these are very good applications, but they don't need to be used everywhere, and there are other applications that can also be successfully used. And so a couple years ago, we started talking about FDR, or full depth reclamation. So what full depth reclamation does is it reclaims, stabilizes, and compacts anywhere from 8 to 14 inches of an entire pavement structure. So that includes the bound material, which is on the very top. It includes unbound material, which is usually some sort of granular material, and it can even go down into the natural soil. So you have a large amount of material that could potentially be milled with FDR. And then you generally, unless you have really high quality in-place aggregates, you generally have to stabilize that with either an asphalt emulsion, an asphalt foam, or a Portland cement. So after you've stabilized it, you compact it, and then you place some sort of surface on top of there. Anything from a chip seal to a micro to an overlay. And this process can lead to a decrease in virgin materials, so you're not hauling in new aggregates and new hot mix, and this leads to some both economic and environmental savings. So we were tasked with taking a look at how can we look at the use of FDR compared to these traditional maintenance and rehabilitation techniques over a lifespan of a roadway. And in order to do that, we followed the life cycle cost analysis procedure put out by the Federal Highway Administration. So if you Google life cycle cost analysis procedure, FHWA, the document will come up. You can download it for free as a PDF. And what we did is we used this report in order to determine what steps do we follow in our life cycle cost analysis. Because I guarantee you, I could come up here next week and give almost a completely different presentation using different assumptions based on our life cycle cost analysis. So we tried to remove as many of those assumptions as possible by following this guideline. So the first step to a life cycle cost analysis is to establish the alternative pavement design strategies. So are you going to look at FDR? Are you going to look at remove and replace? Are you going to look at just a chip seal? And then you need to determine what sort of performance periods do you need. So how often are you going to apply these chip seals? How often do you need to do an overlay over your performance period, which we chose as 50 years? You then need to estimate both the agency costs. So this is essentially how much it costs to build these roads or maintain these roads. But then you also want to incorporate the user costs, because depending on which application you use, you may need to close the road for a longer time period, or you may need to go from 2 lanes down to 1 lane for a longer time period, and there can be some delays associated with that. So we also incorporated that a little bit. The 5th step is to develop expenditure stream diagrams. This is a nice way to graphically represent your different options. And with these expenditure stream diagrams, you have expenses over a 50-year period, and you want to take all of these expenses and bring them back into year zero, into today's dollar, and we call that computing the net present value, or MPV. And then finally, you can analyze your results, you look at your different strategies, and you can reevaluate what you want to do moving forward. I'm going to go through an example from the state of Arkansas using all 7 of these steps, but I feel that 1 through 5 and step 7 are relatively straightforward. They're kind of just making very discrete choices or choosing between A and B, but I did want to spend a little bit on slide 6 here, and there will be a test afterwards because this is the only equation you'll have. This is how you compute the net present value of a material. You first take your initial cost. So this is essentially what the agency cost is to construct the roadway. Then you have to determine what sort of maintenance you need and what sort of rehabilitation you need. So are you going to apply a chip seal every 7 years? Are you going to do a mill and fill every 11 years? After 25 years, are you going to have to do some major rehabilitation? So this goes into how do we make assumptions? What are we assuming that we're going to have to do for the next 50 years, which is not an easy thing to do. And you take these maintenance and rehabilitation costs and you bring them back to today's dollar amount. And you do that using R, which is your discount rate, another assumption, what value do you assume for the discount rate, and T, which is your time period. So what year are you going to apply it? And you can bring those maintenance and rehabilitation costs back to the present. And then finally down here at the end, you actually subtract your salvage value. We're lucky to be in an industry where our in-place materials have value. If we mill up our in-place materials, that can be used as wrap materials in future jobs, potentially. So our salvage cost, we actually subtract that because that's some sort of benefit that's coming down the road. And if you take your initial, you add your maintenance, you add your rehabilitation, and you subtract your salvage, you can get a single number. And that single number is your net present value. Now, I do want to spend a little time talking about salvage costs because I think that this is another thing where people aren't quite sure how can we quantify the value of our roadway in year 50. We got this equation from the Asphalt Institute. They had a nice article a couple years back about computing salvage cost, and this is what we used. We said that the salvage cost was the CLR, which is the cost of the last resurfacing. So for example, some of these analysis in year 44, we did an overlay. So at year 50, that is 6 years after that last resurfacing. And you multiply that value by the remaining life over the service life. So that's just basically how far into that strategy have you gone. So if it was 44, then that would be 6 years in the numerator. And if it's an 11-year strategy, it'd be 6 divided by 11. And then you add on the CIR, the cost of the lower asphalt layers remaining from initial construction. So that's how we calculated the salvage value, and that was subtracted. Now, to kind of transition into the example, we're going to go through those 7 steps of the FHWA life cycle cost analysis procedure. So the first thing that we want to do is we want to establish our alternative pavement design strategies for our analysis period. And then second, we want to determine the performance periods and activity timing. As I've mentioned, the traditional design strategies for pavement maintenance in Arkansas is chip seals, 2-inch overlays, mill and fills with 2-inch overlays, and then remove and replace. Now there are a couple things I want to point out here. These 4 are the 4 traditional methods of maintenance and rehabilitation in the state of Arkansas. And these years afterwards, this is the activity timing. So in this analysis, we assumed that if you're going to place a chip seal for a 50-year life, you would need to place a chip seal every 6 years. So that's where this number came from. For the 2-inch overlay, we assumed every 11 years you would have to place a 2-inch overlay. For the mill and fill, we assumed every 11 years you'd have to mill 2 inches and place 2 inches. And then for removal and replaced, we assumed every year we would mill and fill that remove and replace in order to maintain the roadway for 50 years. And we got these numbers. The state of Arkansas generally does chip seals every 5 to 7 years, and they generally do a 2-inch overlay every 10 to 12 years. So that's how we got that 6 years and 11 years. Now for full depth reclamation, what we're assuming is we go into our roadway, we perform that FDR process, we mill all that material together and we place it down, and then we do one of two things, and you'll see two different analysis numbers. We either use every 6 years, you place a chip seal, or you'll also see numbers where every 11 years you put a 2-inch overlay on it. So we did both examples, and I'll go into that when we get into some actual numbers from our analysis. And then as I mentioned, it is a 50-year design, and we had to assume that the non-surface layers were structurally sound. This is a huge assumption. Anyone here see a road last for 50 years with no structural problems? No? No. But it's an assumption, and it's an assumption we had to make. So we assumed that none of the FDR sections would have structural problems. We assumed none of the remove and replace it have structural problems, those type of things. And there's no deterioration of the structures. So we're just assuming that we're putting in a high-quality, structurally sound road, and we're essentially just maintaining the top of that layer for the 50 years. This is an example of an expenditure or a pavement condition versus pavement life graph. And the nice thing about this is it graphically shows the difference between doing, for example, a chip seal and a 2-inch overlay. So in theory, when you're placing a chip seal, every 6 years, the quality of the roadway is going down to around what we call the terminal serviceability, which is where the roadway needs some sort of maintenance or rehabilitation. You apply a new chip seal after 6 years, the pavement condition increases again. And you can see every 6 years you have this pattern. And with the 2-inch overlay, we assumed every 11 years you placed a 2-inch overlay. So when you place those 2-inch overlays or the chip seals, the quality of your pavement, the pavement condition, returns to that initial level. Now, obviously, this is an idealized graph, but it kind of helps people understand what are we doing when we're applying these maintenance and rehabilitation treatments. So we did our analysis, our life cycle cost analysis on 4 different highways: Arkansas 98, 134, 36, and 5. So these are 4 state highways across the state of Arkansas. And if you're reading from the left to the right, you have an increase in traffic moving from the left to the right. So Arkansas 98 had the lowest traffic, Arkansas 5 had the highest traffic, and then the existing pavement structure thickness of bound material is also increasing. So the thinnest roads were on the left, Arkansas 98, and the thickest road was on the right, Arkansas 5. Now comes the fun part, trying to assign some dollar amounts to each of these maintenance and rehabilitation techniques. The state of Arkansas is very generous with the numbers they provide online. So if anyone wants to, you can go online to arkansashighways.com and look at the bid prices for every single construction job in the state of Arkansas. And one nice column they have is a weighted average. So you can see over the entire state, over all the jobs, what is the weighted average price of, for example, a chip seal. So what I did is I took the polymer modified emulsion and I took the aggregate chip and I just added those prices together. And these are the weighted averages from across the state. And all of the numbers here you'll see in the right-hand column going down here, this is cost per lane mile in 1,000s. So our chip seals cost approximately $12,000 per lane mile, and this is from the weighted averages. Our 2-inch overlays, assuming that we used 5% asphalt binder and 95% aggregate, was approximately $65,000 per lane mile. The mill and fill, this is essentially the 2-inch overlay, but then we also added the cold milling process, again from the bid sheets, and that was approximately $77,000. The removing and replacing in the FDR, this becomes a little more complicated because the chip seal, the 2-inch overlay, and the mill and fill are not intended to add structural capacity to a roadway. Well, a 2-inch overlay does add structural capacity, but when you're doing remove and replace and when you're doing FDR, you can significantly change the structural capacity. So who here is familiar with the 1993 AASHTO design guide? So a couple people, if you remember the structural layer coefficients in that equation, do I have an hour to talk about that? No, okay. So basically, the remove and replace and the FDRs, you can actually increase the structural capacity by modifying those structural layer coefficients, which is a great topic to talk about, which unfortunately we don't have time for now. But because remove and replace and FDR can change that, depending on the structural capacity you want, and I'll show a slide on that up here in the future too, you can spend anywhere from $264,000 to $502,000 per lane mile for remove and replace, and then anywhere from $78,000 to $218,000 per lane mile for FDR. Those are the agency costs. Now, we also tried to look at the user costs. So you're going to see a very similar slide as the previous one, but instead of showing agency costs, we're going to show user costs. So the user costs were a function of auto delay, so personal vehicles, truck delay, which is more of commercial vehicles, and also the production rate. So how long do you need to physically close a section of road? And we assumed that we were essentially just taking one lane of capacity out of that roadway. All of the roads that we looked at were two-way, which means that if you closed one lane, you would have to do traffic control on that second lane, but you can kind of scale this up if you'd like. So for the chip seals, again, using that emulsion and aggregate, we assumed that it would cost anywhere from $4,000 to $63,000 per lane mile based on user cost. And you can see here, this range, $4,000 to $63,000, that's a huge range of user costs, and that is dependent on how much traffic you have. So the lowest traffic, Arkansas 98, had about, off the top of my head, I think it had 400 ADT, and Arkansas 5 had about 4,000 ADT. So the more traffic you have, the more people that will be delayed. The more people that are delayed, you have your higher user costs here. For the 2-inch overlay, it's 5 to 76, and the mill and fill is 21 to 310. And this is where things get really cattywampus in my mind. With the remove and replace, it's anywhere from $48,000 to $709,000 per lane mile. So not even looking at the agency costs, if you just think about the cost to the drivers on the road, removing and replacing a 2-lane highway, we estimated could cost up to $709,000. And I'd be happy to share the spreadsheet that I developed in order to calculate that number, because of course I had to make assumptions, but user costs are a significant amount of our road costs. And then FDR is even more wider of a range, $16,000 to $827,000, because we compared asphalt emulsion, asphalt foam, and Portland cement. So one of our assumptions was the Portland cement took 6 days to fully cure, to have that water fully hydrate with the Portland cement. And I guarantee you half of you in this room could argue with me on that 6-day number, but we just had to make an assumption. We had to move forward with it. So this is the user cost that we had. So moving on to the expenditure stream diagrams, when we see these numbers actually come into play, this is an example of a chip seal versus a 2-inch overlay and the costs that are associated with that. So if you recall, we mentioned that we were assuming a 50-year analysis strategy. So at year 50, that's when our analysis ends. For chip seals, every 6 years, we were placing a chip seal. Every 11 years, we were placing a 2-inch overlay, and we had this 5% discount rate. So we're assuming in year 6, we would spend $12,000. But if you bring $12,000 from year 6 back to year 0, which is today's dollars, that is actually represented by about $9,000. And as you go further into the future, because that denominator is getting bigger in that one equation that I showed, that number is going down. And when you sum all of these up, that is what your net present value is. And then you can see down here the salvage value. We would actually subtract that from all of these maintenance costs in the up to year 50. So you can show this in a table form, or you can show it in a graphical form. And this is an expenditure stream for just a chip seal. And you can see here your agency costs are on the bottom and your user costs are on this top. So every 6 years, you have both these agency and user costs, and all of these arrows pointing upward are positive costs. So this is the cost of the maintenance of placing the chip seal. And then right here at year 50, you see this little 1.1. That's the salvage value. And if you recall, you subtract that from your net present value. So you take all these upward arrows, add them together, take them to year 0. You take that one downward arrow, you subtract that, push it to year 0, and that gives you the net present value. And that's what we're going to finish up here, is looking at the net present value. So I've been hollered at for showing this slide before because it is just one example, and people who've worked with FDR have said, oh, our numbers look nothing like that. And that's fine. These are the numbers that we calculated from our analysis using the AHTD or ARRA prices. So this is the agency and user costs, and this is the net present value. So this is looking at the 50-year lifespan, all of those brought back to year 0 into one number, our net present value. And you can see here we're ranging from a chip seal, which is at about $36,000 or so, all the way to a reconstruct. And you can see here that we have min and max. And that's assuming a minimum structural number is one end. So that, I believe, was an 8-inch depth. And then a maximum, I think, was the 14. Maybe it was 6 and 14. But basically look at a minimal structural capacity and a maximum structural capacity. Obviously, the maximum structural capacity will cost more because it's thicker. So in order to highlight two things on this slide is this is what ARRA was very interested in, is full depth reclamation is very competitive. In fact, if you do the minimum reclamation depth of 6 inches and you put a chip seal on there, that is cheaper than milling and overlaying Arkansas 98. So this is the lowest traffic volume and the thinnest pavement layer, and FDR is actually cheaper than doing a mill and fill. So this is a great alternative on this lower volume, thinner road. And then you can see here, if you want full structural capacity with 2-inch overlay, that is actually cheaper than even the minimum reconstruct. So AHTD loves going out and ripping out a road and building a new road. And people like it, lots of things are being done, really shows a big difference, but we're just trying to say that may work on some roads, but on others, FDR is actually a more economically competitive alternative. And I wanted to show the other extreme. This is on Arkansas 5. So this had the highest existing bound pavement material, and it also had the highest traffic. And you can see here, the minimum FDR is not quite as competitive. In fact, while it's still cheaper than a mill and overlay, it's actually a little more expensive than a full reconstruction with the minimal structural number. And then the maximum FDR with 2-inch overlay is actually more expensive than a reconstruct, the maximum reconstruct. So on your highest traffic, thickest layers, FDR is not as competitive. So from an academic perspective, I think it would be fascinating to try and optimize this project, optimize the traffic and the pavement thickness. So if anyone wants to sponsor any research, anyone? I'd be happy to do it. Just talk to me afterwards. It is a joke, sorry. Tough crowd, and I only got 2 minutes left. So here is a summary, and I apologize to those in the back. If you can't read this slide, there's a whole empty road up here. You can get up closer. But here is just looking at emulsion FDR, foam FDR, and cement FDR. And you can see the cost per lane mile, and this is just the user costs. Oh, excuse me, this is just the agency costs for a chip seal surface. And you can see that these are all relatively the same. Cement FDR is actually a little bit cheaper, but they're all kind of in the same ballpark. But when you start adding the user costs, especially on Arkansas 5, which is the highest traveled road and the thickest structure, that's when the user costs start dominating and really start changing the picture. So I believe this slide is going to be on a website or something, so you'll be able to take a look at these numbers more closely. If you want, you can shoot me an email too. But this just graphically shows how on this Arkansas 5, the user costs really start differentiating the benefits to FDR on the 3 different FDR stabilization types. And then my last couple slides here about graphs is just showing, I talked a little bit about structural capacity and thickness of roadways. You can convert that to amount of traffic. And that's a little more easier to wrap your head around, is how many easels or equivalent single axle loads can go along there. And you can see here, if you just put a chip seal on all those 4 roads, Arkansas 98, Arkansas 134, Arkansas 36, and Arkansas 5, putting a chip seal on really doesn't do anything with increasing the amount of traffic you can have. But if you do an FDR, when you start reclaiming down to 12 inches and especially 14 inches, you really see the benefits of using FDR and the increased structural capacity that FDR provides. And the structural capacity can be translated into an increased amount of trucks and easels that can go on the roadway. And this is mitigated a little bit when you're comparing it with an overlay. So if we put a 2-inch overlay on those 4 highways, especially on Arkansas 5, which had the most traffic and the most bound material, putting a 2-inch overlay does bump you up significantly with capacity. But again, you can see FDR, especially at these thicker layers, becomes a lot more competitive. So in conclusion, we looked at FDR versus essentially chip seals, 2-inch overlays, and mill and fill. FDR was quite competitive when you had thinner in-place bound material and lower traffic, and that started tipping as you got thicker in-place material and thicker traffic. The second thing I'd like to point out is when you do start incorporating user costs into our analysis, it really does change what's going on with the overall costs. So if we do start incorporating user cost into our life cycle cost analysis, that will significantly change the dollar values. And then finally, FDR really does increase structural capacity, which translates into more traffic as you get greater than 10 inches. So I appreciate your time. I'd be more than happy to take any non-football related questions. Yes, sir. Could you define incremental cost for me?
It's a process where you take each of the competing alternatives, stepwise calculation, starting with what looks like the least cost. And then you have a defender, and then you have an attacker. You progressively do that. So it becomes a dynamic approach. So comparing the alternatives.
Yeah. We have not. We saw this as a very first step, and it was very simplified. We didn't, because I think you're talking kind of about a second or third step where it becomes a little more dynamic, because obviously if you do one thing, that could influence multiple things down the road. But if you choose another option, that will influence things differently. And we haven't had a chance to dig more into that cause and effect, but I think that would be a fantastic idea. Yeah, thank you. Yes, sir.
Have you used any LCCA software like Real Cost or Darwin?
So the question is, have we used any software? And we just used Excel, because it's my humble opinion that all those softwares are essentially glorified Excel. And I love using Excel. I don't know if any of you are engineers, but I think it's so much fun to like try and make things efficient and do as little work and get as many numbers as possible. But we just used Excel. Yes?
Could you, just intuitively, I'm trying to figure the mill and fill with two lasting 11 years, remove and replace only 11 years, like the same. Is that because you end up with less asphalt structure, or what's intuitively the reason they're the same?
Right, so the question was, why did we assume an 11-year performance period for both 2-inch overlays and mill and fill? It's because I came at it from the mindset that the pavement deteriorates at the same rate. So whether no, so for the remove and replace analysis, we assumed that every 11 years we would put an overlay on top. That was the maintenance strategy. We wouldn't remove it and replace it every year. It's just that after 11 years we would put oh, I can't remember if it was a 2-inch overlay or a mill and fill, but it was the 11-year cycle of maintenance. It wouldn't be a chip seal every 6 years. It'd be a mill and fill every 11 years, yeah.